Hi, it's me, Dr. Prasad Puthiyillam. Continuing my classes on coordination chemistry. This is class number 5. In previous classes, I explained or given the introduction to coordination complexes, the transition metals, structure of complexes, then ligands, various types of ligand, the weak field ligand, strong field ligand, then introduction to magnetic behavior, that is types of magnetic behavior, how they are classified as para, dia, ferro, ferri, as well as anti-ferro magnetics. Then this is a continuation of that. This class is a continuation of that. Okay, here I will be explaining about the crystal field as well as ligand field theories, the splitting of orbitals. Okay, so splitting of orbitals that is supported by the crystal field theory. Whenever in presence of a ligand, what will happen? Okay, so it is given the crystal field theory states that d or f orbitals degeneracy can be broken by the electric field produced by ligands stabilizing the complex, and the degeneracy is broken due to the static electric field produced by surrounding charge distribution. Electrons in d orbitals of central metal ion and those in the ligand repel each other due to repulsion between like charges, and therefore d electrons closer to the ligands will have a higher energy, results in the d orbital splitting in energy. Okay, let's see one by one. So degeneracy or degenerated orbital, that means the orbitals which are having same energy. So in d we write it as a 5 dxy, dyz, dxz, dx square, 2y square, dz square. All those 5 are having same energy. We call it as degenerated orbital. Likewise in F also. So in presence of a ligand, that degeneracy will be broken. It will be splitting. Splitting takes place. That is because of the static electric field produced by the charge distribution, surrounding charge distribution. That is the ligands. Ligands we treat as the charged points. Okay, so those charged points will create a static electric field, so that this degeneracy of d orbital will split. Okay, so electrons in d orbitals, so central atom, and those in the ligand repel each other. So the metal ion, the electrons in the metal ion as well as the ions present in the ligand, they will repel each other, which creates the increase in energy. Okay, whenever such type of repulsion takes place, that improves the energy or higher energy. It goes to higher energy level, becomes less stable, then try to undergo stabilization. Okay, so the d electron which are closer to the ligand. Okay, we know dxy, dyz, like that, 5 petals are there. Those d orbitals, if any one of the d, either it is dxy or dyz or dx square, I mean dz square, if it is closer to the ligand, then it will be having higher energy. Okay, though these are results in the d orbital splitting energy. The splitting will be affected. How the splitting takes place, which are the parameters which affect the splitting, are nature of the metal. Okay, the nature of ligands surrounding the metal. Nature of the ligand means whether it's weak field ligand or strong field ligand. Metals oxidation state. We know the oxidation state we discussed previous class, +1, 2, +8 oxidation states for various transition metals, and which are the stable oxidation state, that also we discussed. If higher the oxidation state leads to larger splitting. Okay, and the arrangement of ligands around the metal ion also contribute towards the splitting. So if you take an example, say if you discuss in detail about that, the presence of ligands, the electrons of d orbital of metal ion arranges to a higher energy level. Okay, so we know in ground state we write as dx by dyz, dxz, dx square to y square, and dz square, and all are having same energy. Okay, so when a ligand comes, it will shift to higher energy level. Okay, it will shift to higher energy level. We call it as a hypothetical energy level. Hypothetical energy level. So 5 energy levels are represented as such, having same energy. That is hypothetical. Hypothetical means if all the ligands are arranged in a spherical shape surrounding the metal ion. Metal ion at the center, and the ligands are surrounding the metal ion in a almost exact spherical way, such that all ligands are contributing equally toward the central metal ion, or central metal ion feels the contribution from all ligands in an equal way. That means the energy level will split, it will jump to a higher energy level as such. There is no breaking. But we never seen a spherical shaped coordination complex. We seen octahedral complex. tetrahedral complex, square planar, cubic, or even planar, even linear coordination complexes are there. That means it cannot go with a hypothetical higher energy level. We have to think about different, that is splitting only it is possible. Some energy levels variation will be there. Okay, therefore we can say that the octahedral and tetrahedral complexes will split to two higher energy levels than the ground state. Okay, compared to ground state, they are having higher energy level, but split into two, and it is not hypothetical energy level. And other dx other complexes, what we explained about octahedral and tetrahedral complex, it into two. Other geometries, it split into more than two. Okay, it does not mean that they will not split up. They will split into more than two shapes. So even two is there, that is easy for us. So more than two, it becomes a little bit complicated. So we'll take the octahedral and tetrahedral cases first. Okay, so octahedral complexes. Octahedral complex, we know how octahedron is formed. Octahedron is formed by arranging four atoms in a plane. Okay, just like a square, and one atom or one charge center at the top and one below the plane. Okay, so here this represents blue colored dots represents the ligands, and those ligands we have to treat as a charged centers, because ligands they are having charge. So here it is for charged center. Okay, so it is a octahedral. The charge centers are towards the corners of a regular octahedron. Okay, so we can draw that completely. Okay, so it is octahedron. Okay, okay, so that is the shape. You can check the actual octahedral shape, or you can you have your own imagination. This is an octahedral shape. Four charge centers are on the same plane, and two charge centers on above the plane and one below the plane. So if I draw the x, y, z directions, before that I want to draw the d orbitals. D orbital, mainly the dz square. So this is how we draw. I will connect it actually. I will write like this, and you will connect here. Okay, so here I have got some limitations. Okay, so this I can represent as the dz square orbital. So dz square, dz square means it is towards the z orbital. Z orbital means it is not on the plane; it is passing through the plane. Okay, it is just above and below the square plane. This is the square plane, square planar, and this is just perpendicular to that, or it is passing through, or the dz this much is above the plane, and the other part of that dz square, it is below the plane, and it is in the z direction, and even the charge center also there on the z plane. Other two lines I represent x and y axis, and this is the z axis. Okay, so in dz square, okay, again a better image is given here. So this is the dz square orbital that is pointing towards the exactly towards the charged particle or charged ligand. So whenever it is facing pointing towards the charged ligand, it will be getting higher energy because it is closer to that charged particle, charged ligand. Therefore, it is getting higher energy. Similarly, dx square to y square, dx square to y square, it is also pointing. If you draw that dx square to y square in that x y z axis, you can see that they are also pointing towards the charged ligands. So these two orbitals, dz square and dx square to y square, they will be having higher energy level than that of dxy, dyz, dxz in case of octahedral complexes. Okay, therefore I can say that it will split into two different energy levels. One we call as EG level, and the other one is T2g. Okay, and this is the energy difference between these two. What is the exact energy, that I will explain in the next class. And the energy difference compared to hypothetical energy level, what higher energy these two is having, and what lower energy these two are having, and how it balances. The total energy should be same. Energy can neither be created nor be destroyed. Okay, that will be explained in next class. So here it is represented as octahedral crystal field splitting energy, delta O. Okay, so this is the energy required. This much energy is required to split this hypothetical energy level to two different degenerated orbitals. Okay, so we call it as EG as well as T2G. Now what is EG and T2G means? T represents triply and D, and this is Gerald. Here E represents doubly degenerated. Okay, I'll write it and show you. So this is dx square y square and dz square orbitals. These are dxy, dyz and dxz orbitals. Okay, now EG and T2g. T2g, that means T is triply degenerate. That means three orbitals are there. Therefore, we call it as triply. 2, it is representing the d orbitals. In detail I'll explain it in coming classes. Okay, so 2 is representing d orbitals, then 0 4s 1 4p, that will explain in detail. So 2 here something related to d, and g, that is symmetry, or it is Gerard in German word means even. In octahedron, if you take an octahedron and if you check, it has got a center of symmetry. That means our octahedral complex is also having a symmetry. So G represents a symmetry here. Okay, so octahedral complex is having symmetry, whereas tetrahedral complex is not having that center of symmetry. Okay, therefore G even we can use to distinguish between tetrahedral as well as octahedral also. So whenever EG is there, that is something related to octahedral, I can say at this moment. Okay, even cubic case also you use EG term, and so here EG, that represents the octahedral complex. Only E is there, that is tetrahedral, or T2G, that is octahedral, T2, that is tetrahedral. Okay, so E represents doubly degenerate. Okay, so we'll continue with that. So here this delta naught, delta O, not it's not delta naught, delta O, that is octahedral crystal field splitting energy in presence of a strong field ligand. You know which are strong field ligand. The best example is a cyanide CN. It's a strong field ligand. In presence of strong field ligand, the octahedral complexes, the crystal field splitting energy is higher than the energy required for electron pairing. That means this energy difference is higher. If electrons, if you start to fill into these orbitals, this energy level is higher, therefore electrons after filling here to go there, it will try to pair it up here only at dxy dyz dxz. First pairing takes place, then only it go to the higher energy level, because that delta O is higher than the energy required for pairing. Okay, pairing energy we call it as PE. That also will explain in next class what is pairing energy and how it is used. Okay, so here I can say that if it is a strong field ligand is there, then pairing takes place. Okay, at a lower energy level, first pairing takes place. Say example, if I take a d5 system, d5 system means 5 electrons are there in the outermost d orbital of this central metal ion. Okay, so 1 2 3, the fourth one we have to make it pairing, then going to the higher energy level singly occupying, it should undergo pairing, because the delta O is higher than, therefore pairing is easy than jumping to higher energy level. Okay, therefore pairing takes place fourth one and fifth one. Okay, what is d5 system example? If we say, that is also explained in previous class, I grouped them. We discussed the possible oxidation state of transition metals, lanthanides and actinides. Then we grouped them as d1 d2 d5 d6 systems. In that, d5 system consists of mn2 plus fe3 plus, like that, etc. Okay, so those are d5 systems. So in d5 system, if it is a weak field ligand, okay, weak field ligand, we started with iodide, bromide, so halides, they are weak field ligands. Okay, and we seen that spectrochemical series, you can check out, guess out which is a weak field ligand, which is a strong field ligand. So in presence of a weak field ligand in octahedral complex, the crystal field splitting energy delta O is lower than the energy required for electron pairing. That means these are closer to each other, okay. Not as previous one, delta O is somewhat lesser. That means electrons will not go for pairing, first electron will go for singly occupying. Okay, electrons will undergo singly occupying, therefore in presence of weak field ligand, same d5 system, if it is a weak field ligand is there, then 1 2 3 4 and 5, this will be the electron arrangement. That means in presence of strong field ligand, how we write it, d5 we write as 1 2 3, and it's a strong field ligand means pairing takes place. and we can now write the electronic configuration. So this is the electronic configuration after presence of the strong field ligand. The electronic configuration, it becomes T2g5 Eg0. So, okay, so here 1 2 3 4 5, all 5 electrons are there in T2g, therefore it is T2g5 Eg0. Therefore it creates a low spin situation. Okay, so here it is spin paired, here also it is paired, plus spin minus spin, therefore it get cancelled. Only one dxz here or dyz or dxy. Okay, all are same energy level, so only one electron is the spinning. That means it is low spin situation, or we call it as low spin complexes. So in case of octahedral complexes, D5 system with a strong field ligand, it forms a low spin complex. No need to by heart it as such. You can say that such a type of arrangements, if we have to write the electronic configuration, or we need to draw this EG T2G structure electronic arrangement, then we can guess whether it is a low spin complex or high spin complex. So here, in presence of strong field ligand, we are getting a low spin complex or LS complex. In presence of weak ligand, okay, previous one was strong field ligand. In presence of weak field ligand, the electron arrangement will be like this. The electron will go to higher energy level than that of a pairing. Okay, the electronic configuration, if we say, that is T2g3 Eg2. Okay, so here it is singly occupied, singly occupied, singly occupied, therefore a high spin situation. Okay, the electron spin will contribute towards our magnetic property. Okay, so magnetic word again came, so that it is a high spin complex. So high spin situation is there, therefore presence of weak field ligand D5 complex is having high spin complex. They are called as high spin complex. Now we'll go to tetrahedral complexes. So in case of octahedral complexes, we see in both cases weak field ligand and strong field ligand. Tetrahedral complex, so how the shape tetrahedral, we know that of tetrahedron. Okay, so central metal atom, tetrahedron, some I'm trying to draw it as such. Okay, one here and here. Okay, now if I try to connect, so this is a trigonal shape and we are making it a tetrahedron. Okay, the central metal atom is at the exact center of the tetrahedron, and this is the tetrahedral shape, so tetrahedral complex. And this blue spheres represents that of ligands, charged centers. Okay, we call it as charged centers, and this is x y z axis. And in case of tetrahedral complex, if you take that of whatever our dz square that we try to draw in octahedral complex. Okay, so dz square. Okay, dz square. Oh, very good. Okay, so I got the dz square shape. So it is not pointing towards the charge centers. Okay, so this ligand is, if it is on plane, this is also on the plane. This charge center is facing away from us, this is facing towards us, and this one is in between. Okay, therefore it is not facing directly towards the ligand. So dz square is not facing towards the okay, so this is more clear here. So you can see this is the dz, the z direction. Ligands are not in that direction. Okay, so dz square is away from the charged center, therefore it is having less energy. Even dx square 2y square is also away from the charged points, they are also having lower energy. But dxy, dyz, dxz, they are somewhat phasing, or some of the lobes are facing towards the charged center, therefore they are having higher energy. Therefore it is a reverse case than that of a octahedral complex. Okay, the same thing is written here. Okay, so crystal field splitting of tetrahedral complex, if we take from hypothetical energy level, it splits into two, dx square, y square, and dz square having lower energy, whereas dxy, dyz, and dxz, they are having higher energy. They are facing, pointing towards the charge center. Okay, so you can say that this is E, this is T2. Okay, so triply degenerated d orbitals, and there is no symmetry, no G. Okay, so this is E, doubly degenerated. Okay, again this is degenerator. Okay, these three are almost having same energy, therefore we call it as degenerator only. But it is triply degenerated. Here it is doubly degenerated. Now the splitting energy, crystal field splitting energy, we write as delta T. T represents tetrahedron. Tetrahedral crystal field splitting energy is delta T. So in case of tetrahedral complexes, the delta T, if you compare with that of octahedral splitting energy, crystal field splitting energy, it is 3 by 9 times that of delta O. Delta T is 3 by 9 times that of delta O. That means delta T is very less than that of delta O. That means the energy of delta T is very less. That means the electron pairing will not take place. Electron singly occupying will be having more preferences. Okay, that is what it does mean. There are only 4 ligands, and hence the ligand field is less compared to octahedral complex. Also, the ligand approach in tetrahedral complex does not coincide with the d orbitals as in case of octahedral complex. Then as a result of tetrahedral complexes are having high spin complexes, because I said delta T is very less than that of delta O. That means the pairing opportunity will be very less for electrons. It will try to occupy singly first. Okay, because the energy difference is less, an electron can go to a higher energy level, okay, than pairing. Therefore if singly occupied, then that will contribute towards high spin. Single occupied electrons or unpaired electrons are more having high spin than the paired electrons. Okay, therefore we will be getting high spin in case of tetrahedral compound. General cases we are getting high spin, since delta is normally smaller than the pairing energy, or pairing of uh, electron is not preferred. Okay, so this is a typographical error here. Okay, so what I explained, that it is forming high spin complexes. Electrons will be singly occupied most of the time. It will try to occupy singly first, then pairing takes place. Okay. Okay, this is a typographic error, typing error. I while typing I made mistake. Okay. Okay, I'll go to the next one, that is low spin complexes. Okay, so in the case of D5 system, you can say that this will be the state. So this is not a low spin complex, it is a high spin complex. Okay, so in case of tetrahedral splitting, we are having high spin complexes. Okay, singly occupied. Electronic configuration is T2E3. Hypothetical energy level of that of a square planar complexes dxy, dyz, dxz, dz square, dxy, dx square to y square. Okay, so if you take this case, this is the splitting of energy levels in square planar complex. Okay, what I said, only octahedral and tetrahedral we are getting two energy levels. Other than that, we are getting more energy levels. So in detail, we'll explain in coming classes for this. So square planar complex, this is the nature of that. If it is linear complex, we are having this arrangement, dxy, dx square, y square, dxz, dyz, and dz square. In that order the energy level goes. Okay, if you take a image of that, if you consider comparator only is octahedral complex, this is tetragonal structure and square planar. Okay, so I'll take one more. Okay, so octahedral complex, tetrahedral complex, square planar, tetragonal, trigonal, bipyramidal, and cubic arrangement. Okay, so crystal field splitting and magnetic behavior. How the crystal field splitting affect the magnetic behavior? Octahedral complexes may form high spin complex or low spin complex based on the nature or strength of the ligand. Tetrahedral and square planar complexes normally form low spin complexes. Complexes which have more unpaired electrons, usually high spin complexes, show paramagnetic behavior. So that's all for this particular class. So thank you very much for watching, and we will continue in next class. a small error happened in my presentation that I'll take and I'll explain it again. Typing error happened because that it confused the next slide also. So I'll continue, I'll explain it once again. The last portions, you just avoid it. Okay, so that will be explained once again in coming next class.